Welcome back. We're going to continue our discussion on a brand new topic, and that would be aromatic electrophilic substitution. Okay. Now, in sharp contrast to the nucleophilic substitution and elimination we learned earlier, in fact, if you actually go back and go through all the videos, you probably did not see me doing any aromatic compounds at all. Okay. They were primarily primary, secondary, or tertiary compounds, but you would never actually have seen any aromatic compounds there. Okay, and I did that on purpose because so I can make the distinction here when I teach you this topic. Okay, and for making learning easy and to keep one of the reactants constant, only one type of aromatic compounds will be discussed in this topic, and that would be benzene. Okay. Now, if you remember from your lessons on aromaticity, benzene is aromatic because it met all of the criteria put forward for aromaticity. And so, benzene exists in primarily two different types of resonance structure, okay, which is this, or you can move the bonds around and then you'll end up with the other resonance structure for benzene, and that would be this. Now, you do not have to worry which one you should use. I would always give you one of the two structures, but I want you to know that even if I didn't give you one and you have to start with one of the other, one of the two resonance structures, you would end up with the same product. Okay, so the only one of the reactants would always be constant throughout this entire discussion, and that would be benzene. It's only the other two reactants that would change, which result in the formation of an electrophile. Okay, which takes us to actually what is an electrophile. Okay, just like a nucleophile, which is a Lewis base and it's electron rich, an electrophile is any molecule, ion, or atom that is electron deficient. In other words, a electrophile is a Lewis acid. Okay. So in sharp contrast also to how we defined a nucleophile, you could actually start with the nucleophile, such as a sodium methoxide, sodium ethoxide, methanol, ethanol, water, ammonia. On the other hand, electrophiles are not naturally available. You would have to make them during the course of the reaction, and then the electrophile then reacts with the benzene to actually make the desired product. Okay, so it's essentially a multi-step reaction. Okay, an electrophile is not available to start with. You would have to produce the electrophile during the course of the reaction, and the electrophile then reacts with the benzene to produce the desired product. Okay, now you do not have to memorize any of these. However, I will tell you which ones you may have to just remember in case if you're one of those people that tend to forget things. Okay, now alkyl ion is one of the common electrophiles used. Okay, now we would discuss each of those in great detail in the rest of the videos, but typically an alkyl ion is a electrophile, which is CH3 plus or CH3CH2 plus, whatever it is, but it's just you have linear increase of carbons with a positive charge, and that's an alkyl ion. Okay, now we would also see how we generate this in each of the successive videos, and we would produce this particular one. I'm going to switch colors here because we don't want it to be all blue here. Maybe green, maybe this different shade of blue. Now this we would produce when we react sulfur trioxide plus sulfuric acid. Okay. Again, as I said, benzene is one of the reactants. You would still need other reactants to produce your electrophile. So this would produce your electrophile in the course of the reaction. Similarly, nitronium ion is produced by nitric acid, which is a strong acid, reacting with sulfuric acid, which is also a very strong acid. Okay, So when these two react together, you produce NO2 plus, which then reacts with the benzene ring. Okay, acyl ion are nothing but, again, just like alkyl, okay, basically you could produce CH3CO plus. You see the plus charges on the carbon. Or if you started with CH3CH2 COCl, then you could have CH3CH2 C plus O. Its R is what is changing, but the C plus O stays the same. And now this is called a Friedel-Crafts acylation. You will see it as we begin to discuss this topic in more detail. So these are the acyl ion electrophiles. And then obviously your halogens. You are so used to seeing your fluorine and chlorine as negative because they are electronegative. But when a fluorine reacts with, say, FeCl3, FeF3, fluorine, you should be very careful that whatever you start with will also have to be present in the iron molecule. So this means you would end up with F plus Fe F4 minus. So if you're starting with, say, Cl2, to produce the electrophile, you would have to use FeCl3, which then would produce Cl plus FeCl4 minus. You see that what you start with should be also present in the iron molecule. Okay, now these are the various electrophiles that we are going to discuss. One video for each. That means we'll have 5 quick videos on these. And some of the key terms that I want you to remember or take away from this whole entire discussion would be, what is an electrophile? Okay, and then resonance structures, which we will see. Effect of a substituent. Okay, what we are going to do is we're going to do 2 things. Okay, by adding an electrophile to a plain benzene ring, we're going to call that a substituent. Okay, so you're going to take a benzene ring which has nothing to it, like it's shown here. This is a plain benzene ring, and you are going to add an electrophile which makes it a substituent. Okay, you're going to add a substituent, and then the substituent will have its own effect on, say you try to add another substituent to the molecule containing an existing substituent, then the existing substituent has some effect on the incoming substituent. And we're also going to talk about, the substituent behaving as an ortho, para, or meta directors. That is, you take a benzene ring, now you added an electrophile as a substituent onto the benzene ring. Let's say you try to add another substituent, then that substituent has an effect on where the incoming substituent would go, and that's what we are going to deal with in terms of ortho, para, or meta directors. And I want to summarize this video by looking at what is the overall scope of what we are trying to do. So here's your benzene ring. See? Okay, here's your benzene ring. And basically all hydrogens are identical. Okay, we're only going to focus on this one. It doesn't mean that it is the only one that you always have to choose. A benzene has 6 hydrogens. They're all identical. In this case, we took a benzene and we added an acyl ion, which led to acylation. Now this is the substituent. Okay, this is plain benzene. We added R C plus O. This is the electrophile, which led to acylation. Okay, now R could be anything. Okay, it could be CH3, it could be CH3CH2. It's the C plus O that's important. Keep in mind the plus charges on the carbon. So this is an acylation. Now this is a substituent. You could add additional substituents to this molecule. Okay, this molecule, you could add additional substituents to this molecule. Okay. Now, what I mean by ortho, para, or meta is something we would learn as we get closer to understanding it. But this is an existing substituent. Let's say I try to add another substituent onto the ring. This substituent that's already present governs where that incoming substituent goes. Does it go to an ortho position, para position, or meta position? I know we have not talked about any of those, but I just want you to know just the overall effect of an existing substituent. Now in this case, again, if we had just added an R plus, like we said, R could be anything, then we are going into an alkylation. Now this is the existing substituent on this molecule. So an incoming, another substituent is governed by where this governs the incoming additional substituent. Similarly, this is what we meant by when we had S plus O3H substituent. This, when reacts with the benzene ring, you produce sulfonation. And then this is what we meant by NO2 plus. Yeah. So this is the substituent currently on the ring. And then you also had Cl plus. If it is Cl plus, then this would be Cl. If it is Br plus, then this would be Br. So basically, you're substituting the hydrogen with a wide variety of electrophiles, okay? And once the electrophile attaches to the ring, the electrophile that's already attached governs, like for instance, say you add a Cl to it, the Cl now governs, if you add an additional substituent, the Cl governs where that incoming additional substituent would go, okay? Now this is where I want to stop the video, because this is basically getting you into the idea of what an aromatic electrophilic substitution would be. Okay, all this would make even more sense as we actually do a real reaction for each of the 5 different kinds of electrophiles that I have shown and have discussed in the previous screen. Right? So stay tuned for further videos.